Okay, in this lecture we're not going to cover new material, we're going to practice what we learned in the previous lecture because it's really important. Okay, mathematical induction, really important. Let's review the concepts and then we'll practice using it some more. Okay, we'll label this proof by induction. Okay, and remember, when you can use this, you're trying to prove, let's write this down. Well, here, let's write it like this. So the goal is prove that some statement, let's just call it P of n, is true for all integers n starting at some point. Let's say, I'm not sure what I used in the last lecture, but let's just say starting at hang on a second. Okay, I just looked in the last lecture I used an A here. So prove that some statement P of n is true for all integers equal to or greater than A. Okay, and so step one is prove or show that, whichever words you want to use. I think I used the words show that in the previous lecture. So show that P of A is true. Okay, and then step two, show that if P of k is true for some integer k, then P of k plus 1 would also be true. Okay, and how do we do that? So you suppose P of k is true for some integer k equal to or greater than A, and then you use that to show that P of k plus 1 would also be true. And that's the whole thing right there. It's got three parts. There's this part right here, and I will remind you that that's called the base case, and it's usually fairly easy. Okay, and then there's this part right here that has a name. That's called the inductive hypothesis. And it requires zero work. It's simply a matter of writing down a statement. And then the third part is right here. That's where the work is always involved. Sometimes it's a little bit of work, sometimes it's a bit more. It doesn't have a name for that last part because it's not a single step. It usually takes a few different steps. The base case usually takes just one step, maybe two. And the inductive hypothesis is just one sentence. So those are very short, so they have names. The yellow part doesn't have its own name because it differs from problem to problem quite a bit. But a proof by induction is always those three steps. Or I shouldn't say those three steps because I labeled them as step 1, step 2. So I should say those three parts, okay? Blue, green, yellow, those three parts. And the way I've labeled it, green and yellow together make up step 2. Okay, and this is all in the previous lecture. Do you remember that? Nothing's new here. I'm just reminding you. Okay, so let's practice. Here we'll do a few proofs. Okay, so here's a proposition. This is in our textbook on page 260. It says, for all integers beginning with 0, so for all integers n equal to or greater than 0, 2 to the power 2n minus 1 is divisible by 3. Okay, let's prove that. First, let's check it and see if it sounds reasonable. If you did 2 to the power 2 times 0 minus 1, what would that equal? That would be 1 minus 1, which is 0. Is 0 divisible by 3? Yes, it is. 0 divided by 3 equals 0. If n equals 1, you would have 2 to the power 2 times 1 minus 1, which would be 4 minus 1, which is 3. Is that divisible by 3? Of course it is. When n is 2, you have 2 to the power 2 times 2 minus 1, which is 16 minus 1, which is 15. Is that divisible by 3? Yes, it is. So it's looking to me like what they said is probably true. Every time I put an integer up here equal to or greater than 0, I appear to get something that's divisible by 3. Okay, so at least I believe what I'm trying to prove. That's always helpful. Now let's see if we can prove it. Okay, so what's the first part? We want to show, by the way, here's P of n right here. Oh, sorry. This whole thing right there. That is our statement, P of n. It's an open statement. Okay, so I want to show that P of 0 is true. That's the first part. Okay, show P of 0 is true. Okay. All right. Well, actually, I already did that. Didn't I? I erased it now, but we worked it out already. I'm just going to write it down here neatly. Notice that 2 to the power 2 times 0 minus 1 equals 1 minus 1, which equals 0. And then I'm going to write comma, which is divisible by 3. Okay, so that's our base case. Now, our inductive hypothesis, which is suppose P of k is true for some integer k equal to or greater than 0. Okay, it's just a matter of writing it down. Suppose 2 to the power 2k minus 1 is divisible by 3. For some integer k equal to or greater than 0. Okay? And then the third part, show that P of k plus 1 must be true. And this is where the work is involved, so you might need to slow down and think about how you're going to do this before you actually start writing the proof. Okay, so why don't we do a little bit of Scratchwork and see if we can figure out how this is going to work. Okay, let's just do a little bit of Scratchwork. So we're gonna be writing down 2 to the 2 times k plus 1 minus 1, and we're going to hopefully show that that's divisible by 3. So let's work this out here. That would be 2 to the 2k plus 2, right? Minus 1. I'm just going to see where this takes me. I can rewrite that as 2 to the 2k times 2 squared minus 1. Okay, 2 squared is 4, so let's do that. Okay, where can we go from here? Well, look at this. We're trying to show that this is divisible by 3. So let's do this. Let's write 4 as 3 plus 1. Okay, now I can see where things are going to go. So this will be 2 to the 2k times 3 plus 2 to the 2k. In case you don't see this, I'm distributing right now. Okay. And then we'll have the minus 1. Okay, now look at this. This part is divisible by 3 because it is 3 times an integer. So that's divisible by 3. This part is divisible by 3 because of our inductive hypothesis up there. So the first part equals 3 times something, 3 times this. The second part equals 3 times something. I don't know what it equals 3 times, but it equals 3 times something because that's our inductive hypothesis. So we will give it a name. Let's just say, well, let me look here. In the book, they call it R, 3 times R, so we'll use that same name. So we're going to want to state this beforehand so that we can use it here. Okay, let's remember that. And so then we're going to end up with 3 times 2 to the 2k plus R. So that is 3 times an integer, so it's divisible by 3. Okay, that's how that's going to work. I'm going to erase this now and we're going to write it neatly. If you need to come back and see the Scratchwork, then you can rewind the video. Okay. All right. So, where we left off, I'm going to pick up right there. Suppose 2 to the 2k minus 1 is divisible by 3 for some integer k equal to or greater than 0. And I'm going to say, then 2 to the 2k minus 1 equals 3 times r for some integer r. Okay, thus 2 to the 2k plus 1 minus 1 would equal, and now I'm just going to write down what we worked out in our Scratchwork. Okay, that would equal 2 to the 2k plus 2 minus 1, which is 2 to the 2k times 2 squared minus 1, which is 2 to the 2k times 4 minus 1, which is 2 to the 2k times 3 plus 1 minus 1, which is 2 to the 2k times 3 plus 2 to the 2k minus 1, which equals 3 times 2 to the 2k plus 3 times r, which equals 3 times 2 to the 2k plus r. Hence, 2 to the 2k plus 1 minus 1 is divisible by 3. And we're done. There's the whole proof. Okay? All right, let's do another practice problem. Okay, let's look at this proposition. For all integers n starting at 3, 2n plus 1 is less than 2n. Okay, so let's prove that. Now, this is a really good example because most people will write some stuff wrong here, and that's good to see that. I want to point it out to you so you don't write it incorrectly. Okay, there's a couple of mistakes that people almost always make in a problem like this. Okay, so pay close attention so you don't make these mistakes. I will point them out to you. Okay, so the first step is to show that, remember now, our base case here is 3 when n equals 3. So we need to show that 2 times 3 plus 1 is less than 2 to the power 3. That's what we need to show. Now, here's how most people write it, and it's not correct. They do this. Well, here, before I even write it down, let's do some scratch work. Okay? Let's see what we're working with here. We've got 2 times 3 plus 1, and we want that to be less than, I'll put this in gray because I don't know that it's less than until I work it out, but I want it to be less than 2 to the power 3, right? Well, what is on the left? On the left is 6 plus 1, which is 7. Okay, that's good. And on the right is 2 to the power 3, which is 8. Oh, that's good because 7 is less than 8. I'm going to put that as black because I know that that's true. Okay, now, that was some scratch work, right? Here's what most people do wrong. They write that scratch work right here. And they think that that's the proof. This is wrong. And here's the reason why. I'm trying to prove this, correct? You agree with that? Okay. And In our society, this is just the way it is. We read how? From left to right, top to bottom. Correct? So your proof needs to work from top to bottom, because that's how we read writing that's on paper. If you want to do it in another direction, bottom to top, you certainly can, but you have to make that clear. Okay? Now, here's the thing. I have circled in red what I'm trying to prove. As soon as somebody starts reading, they see, oh, 2 times 3 plus 1 is less than 2 cubed. So first of all, they might have a question and they might say, okay, why is that true? I need to work it out. Here's the even bigger problem. They look underneath that and they see a 7 and an 8 and they say, why is there anything written under there in the first place? Because we read from top to bottom. And I'm trying to prove this in this case. In the base case, I'm trying to prove that base case. So if I already have it here, then why is there another line below it? I apparently have already reached the thing I'm trying to prove. So why are there numbers written below it? You see the mistake? So there's 2 mistakes there. Number 1, the person wrote in yellow what they're trying to prove, but they have not actually proven it. They've just written it down. And number 2, if that were true, that they've already achieved what they're trying to prove, then why is there another line below it? This isn't how we work. We don't say, look at this, and then look at this, and then here, and then here. That's not how we read in our society, in a circle like that. No, that's not how it works. We read left to right, and then top to bottom. So your reasoning needs to be accurate to that direction as well. Okay, now the reasoning here is correct. It's just that the person's not portraying it in the correct order. Here's the order. Here's the correct order that this is happening. This equals this, which is less than this, which equals this. That's the order you need to write it in, because that's the order that the calculations go. So it should be written like this. Two times 3 plus 1 equals 7, which is less than 8, which equals 2 to the 3. And that's why 2 times 3 plus 1 is less than 2 to the 3. You see, the way I've written it now makes sense. The logic flows in the same direction that I'm reading. Okay? That's important. Most people think, oh, that's not a big deal. And most people will just write this. Okay? Well, you're not going to get it marked correct if you do that. There's a difference between scratching out things to figure out what numbers you're dealing with and how they're related. The order in which we figure those out is not always the order that proves things. And that's fine. When you're doing your Scratchwork, scratch it out in any order that works for you. But when you write it in your proof, things need to be logically ordered correctly. Okay, so we're trying to prove 2 times 3 plus 1 is less than 2 cubed. So we write 2 times 3 plus 1 equals 7, which is less than 8, which equals 2 cubed. Okay, very important. All right, now our inductive hypothesis. Suppose 2k plus 1 is less than 2 to the k for some integer k equal to or greater than 3. And then our main part of the proof, then 2 times k plus 1 plus 1. And here's my goal, so I'll write it in gray. My goal is to show that that is less than 2 to the power k plus 1. That's our goal. So let's do some scratch work down there to see if we can figure that out. Okay, so again, I'm just going to write this in gray. We have this on the left-hand side, and our goal is to show that that is somehow going to be less than 2 to the k plus 1. So let's work it out. This is scratch work, so you can write it out in any order that makes things work for you. Okay, so let's see, on the left we'll have 2k plus 2, right? Plus 1. And on the right, what do I have there, by the way? I have, that will be 2k times 2, right? Which might be helpful. I'm not sure. I'm going to write it down for now. Okay. All right, let's go back to the left. 2k plus 2 plus 1. Okay, well, now remember, this is a hint for you. Remember your inductive hypothesis. We know something about 2k plus 1. And here I see 2k, and here I see plus 1. So let's put those together next to each other, because I know something about that. So let me reorder that. So it says 2k plus 1 plus 2, because I know that this is less than 2 to the power k. That's my inductive hypothesis. So, and look, by the way, right here, there's 2 to the power k times 2. Okay, so this will be less than 2 to the k plus 2. Now, when you look at this, when you're doing work like this, you automatically assume that there's equality on each line, right? This equals this, and so on. And that's fine. I mean, that's the way we do things. But notice that when I go from here to here, it's not equal anymore. This does not equal this. The top circle is less than the bottom circle. So I better write that down. I better start to be a little bit more careful, just for my own purpose here, so I don't confuse myself. Here's what I'm going to do. Whoops. I'm just getting some extra space in here. And what I'm going to do is I'm going to write equal signs between these, because they're equal, and these are equal. And it's less than the next one. Okay? Now remember, I'm trying to relate that to 2 to the power k plus 1. Okay, here's 2 to the power k. Here's 2. isn't it true that 2 is less than 2 to the k? So then wouldn't this be less than 2 to the k plus 2 to the k? And doesn't that equal 2 to the k times 2, which is what I had over here. I accidentally erased it. So you see now that bridges the gap. Do you see what I'm saying? That equals 2 to the k plus 1. And here we go. From here to here. I have 2k plus 1 is less than 2 to the k plus 1. Okay? Now again, I'm going to make a big deal out of this again. When you write this down, you absolutely do not write this. Because if you write that, then you're saying you're done with the proof. And every person reading that is going to think, how did you get that? I don't see where it came from. And if you say, because this side equals yada, 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 and this side over here equals this, and you'll see when you get to the end, no, that's not how proofs work. The logic has to be correct in the order that it's written. You can't say, I know that this, logically, there's no explanation for that yet. But if you follow it down, you'll find out that I'm actually correct. That's not how it works. Okay? The logic has to be correct in the order that it's written. Or a better way of saying it is, it needs to be the steps need to be written in the correct order that the logic is. Okay? So I'm starting with this. I want to end with this. The stuff in between should be right here, not down here and here. Okay? Okay, so I actually have it already written down, don't I? We worked it out below. It's right there. Follow that pink arrow. Okay? So we have 2 times k plus 1 equals 2k plus 2 plus 1. Now I've got a couple of choices to make. I can either go like this, which equals 2k plus 1 plus 2, which is less than 2k plus 2. But you see what happens? I'm running out of room, right? If you want to try to fit it all on one line, you certainly can. Let's see how long that would take. All right, I would say, which is less than 2k plus 2k, which equals 2k times 2, which equals 2 to the k plus 1. Okay, so it didn't take too much room. Maybe if I had written smaller, I could fit the whole thing in. And that would be my whole proof. Let's go ahead and erase this gray stuff here. That would be the whole proof. A square means the proof is done. Okay, so that's one way to write it. Okay, what if you run out of room? Okay, then here's a couple of things you can do. I'll give you two options. One is, just like when you're writing a story, what do you do when you run out of room at the end of a line? You use a hyphen and then you go to the next line, right? So we don't use a hyphen in math, but because it would look like a minus sign. But you could take this stuff. Let's just suppose that this part here didn't fit because you came upon the edge of the paper. So you could just take that and just go down here. And there you go. It's still one line here that goes across here and then runs out of room, so picks up again right there. That's not two lines that I just highlighted. That's only one line of the proof. Okay, so that's one way to go. Or if you think it looks nicer, you can go down. So that would look like this. So that would be right here. And then this would be right here. And this would be right here. And then that one. And then that one. That's perfectly fine too. Now, you might be thinking, but you just said not to go down. We go left to right. That's true, but the thing that I was pointing out then that was wrong was that there were two sides. And both sides went down. You see what I'm saying? Look, think back to the base case. Remember, I said don't do this. I said don't do that and expect the person to read in this direction. I said don't do that. That's not what's going on over there in my proof. The direction only goes one direction. From beginning to end. It doesn't go down, over, and back up. That's a no-no. You see what the difference? I hope you do. It's a lot of people think it's not an important difference, but it's hugely important. Okay? So these equations and inequalities here flow from beginning to end in one direction. Okay? Very, very important. And that, by the way, is the whole proof. We're done. I have my base case. I have my inductive hypothesis. And then I have this last part, which doesn't have a name. And we're done. Okay? Okay, one more example. So you've probably seen this before. I'm sure you must have, but I'm going to start at the beginning just in case, okay? So when you see a list of numbers written in a certain order, that's called a sequence. Like, for instance, let's just say 1, 5, 9, 13, 17, and so on. Okay? That's called a sequence. Some sequence can be defined what you could call explicitly. Oh, by the way, let's use some names here. So the first number we'll call A1, and the second number A2, and the second number A3, and so on. Okay? Now, when we say define a sequence explicitly, this is what we mean. It means come up with a formula that I could use to calculate any term that I want. Okay, like an example here would be, for that sequence I could write a sub k equals let's see, 4k minus 3. Do you agree that that formula would work? For any integer k, starting with what in this case? Starting with 1, right? Do you agree that that's true? 4 times 1 minus 3 is 4 minus 3, which is 1. 4 times 2 minus 3 is 8 minus 3, which is 5. 4 times 3 minus 3 is 12 minus 3, which is 9, and so on and so on, okay? Another way to define a sequence is called implicitly, or another word for that is recursively, which is this. You specifically say what the first term is, and sometimes people need to say the first few terms, but in this case, I'll just say that the first term is a 1. And then, instead of giving a formula for any term, what you do is you give a formula for how to get the next term, no matter where you are. Okay? So I would say the sequence starts with a 1, and then to find out any term, so I write a sub k, I tell you what to do to the previous term. So in this case, I would write a sub k equals a sub k minus 1, which means the term right before, plus 4. Okay, and that's how I can find the second term, and then the third term, and then the fourth term. So I write for any integer k equal to or greater than 2. Okay, that's called an implicit or a recursive definition. Both of these, this definition and this definition, those are both definitions for the same sequence that I have written above. Some sequences you can't define explicitly, only implicitly. And some sequences you could define either way. So what we're going to do is I'm going to write an explicit definition and an implicit definition, and we're going to prove that those two definitions will give you the same sequence. Okay, so look at those two definitions there. The one on the left is an explicit definition for a sequence. The one on the right is an implicit or recursive definition for a sequence. We're going to prove that those two definitions will give you the same sequence. Okay, so here's how I'm going to write it. Okay, see how I've written it? Let a sub n equal 2 times 5 to the n minus 1 for any integer n starting with 1. Show that a sub 1 equals 2 and a sub k equals 5 a sub k minus 1 for any integer k starting with 2. Okay, now let me ask you a couple of questions. We're going to use induction to do this. Where does the induction start? What is the base case for the induction? Okay, I want you to think about that. The answer is k equals 2. Because look at this stuff over here. There's two different statements. Whoops, I didn't mean to erase it. I meant to highlight it. So there's this statement, which is, let's just call that blue. Okay, and then there's this statement, we'll call this green. Now, we're going to prove green by induction. We do not prove blue by induction because blue is not a statement about a bunch of integers. Blue is only a statement about one single number. Green is a statement about a whole bunch of integers, so we will use induction to prove green. Do you see what I'm saying? So blue, that is not the base case of our induction. That's something that I want you to notice. Okay, so first I'm going to prove blue by just showing it. I'm just going to show a sub 1. I'm going to calculate a sub 1 and show that it comes out to be 2. And then I'm going to use induction to prove green. And so my induction will start with the base case of 2. Okay? All right, so let's do it then. So, notice that a sub 1 equals 2 times what? 5 to the 1 minus 1. And what would that equal? That would equal 2 times 5 to the what power? 0. What's 5 to the 0? It's 1. So I have 2 times 1. And what's 2 times 1? It is 2. There we go. Okay? Once again, notice I did not do this. I did not write a sub 1 equals 2 because a sub 1 is 2 times 5 to the 1 minus 1, and 2 equals 2 times 1. See, I did not write it like that. I might have worked out my Scratchwork like that. That's fine. And then I want this to be my beginning and this to be my end, so it flows in this direction, right? So the reality is when I write my proof, these equal signs aren't there, they're actually here. So then I unfolded it and I wrote it left to right. Okay, that's important. Okay. Now, that's the end of proving what I highlighted up there in blue. That's done. That has nothing to do with induction. That was just a single statement, and I proved it. Okay, now I'm going to prove what's highlighted in green. And to do that, we're going to use induction. So we have our base case. Where is this induction starting? Starting right there with the number 2. So my base case is when the subscript is 2. Okay, so I'll write. Notice also that a sub 2 equals now I hope to show what? Let's write it in gray. I hope to show that it equals 5 times a to the 2 minus 1. That's what I hope to show. And by the way, 2 minus 1 is 1, right? So it's fine to just go ahead and write a sub 1 there. You don't have to write 2 minus 1. Okay, that's my goal. What do I know about a sub 2? Well, here's the formula they gave me. Do you see what I'm saying? It's important to understand they didn't give you this for a sub 2. They gave us this formula and they said, prove that this will work. So I don't get to use this. You don't get to use the thing you're proving to show that the thing you're proving is true. That's circular logic. Okay, so I should write a sub 2 equals 2 times 5 to the power 2 minus 1 which is 2 times 5 to the power 1, right? Which is 2 times 5. Okay, which equals 5 times 2, right? And the only reason I'm bothering to switch the direction is because I've already shown that 2 is a sub 1. So that is 5 a sub 1. And there's my base case. Okay. Then my inductive hypothesis, suppose a sub k equals 5 a sub k minus 1 for some k equal to or greater than 2. Then, and now I want to write a sub k plus 1, and hopefully that will equal what? 5 times a sub what? K. That's my goal, because k plus 1 minus 1 is k. Let's see if we can make that happen. Okay, so where do I start out? Well, I have a formula here. So let's use it. So a k plus 1 will equal what? It will equal 2 times 5 to the k plus 1 minus 1. Okay, that's fine. That is 2 times 5 to the k, correct? Now let's write that as 2 times, let me put parentheses. Well, no, that's okay. We don't need parentheses. Let's write 2 times 5 times 5 to the k minus 1. Do you agree that this equals this, right? That's just a simple statement. And then I'm going to swap the order of the 2 and the 5 in front. You'll see why in just a second. Here's the reason I did that. I want you to look at just this part. 2 times 5 to the k minus 1. And also look at this formula that we have right there. Look at that. 2 times 5 to the n minus 1 is an. Then wouldn't 2 times 5 to the k minus 1 be ak? So I have here 5 times ak. Guess what? That's what we were trying to get. We were trying to show that this equals this, and we just did it. Okay? So we're done. That's the proof. Now, this one is in the book, but I will caution you, they've done it differently. It looks very different. And that's because they did things in a different order. What I proved with you here is I proved that this is the same as this. What they did in the book was they proved that this is the same as this. So our premise and our conclusion were swapped, the way I've done it in this lecture and the way it is in the book. Okay, so they're both correct, but they're very different. The way I did it is completely correct. The way it is in the book is completely correct. But if you try to intermingle them and use some of the way I did it and some of the way the book did it, it's not going to be correct. Because I did it with, let me show you again. I've done it with this premise and this conclusion. And so the logic works in a certain direction. The book did it with this premise and this conclusion. The logic works differently. They're both correct, but if you use part of some and part of another, then it's going to be all mixed up and it's not going to work correctly. Okay, that's it for today.